Geology students, um, we took the test and you finished the lab quiz, and we have another test coming up in about 3 weeks, and so we're going to get ready for that. The average grade on the first test was 85, but some of you did really, really good, and some people didn't do so good. If you didn't do so good, you need to really focus on taking good notes when you're watching the videos. Watch the videos twice if you have to. Look up some of these things in your book as well. Use flashcards. Study with someone else who's doing better in the class. And ask questions. I'm always there to answer any questions you have. I really do care that you do well. Do as well as possible. For the lab quiz, most of you all did pretty good, but I just have to mention that some people should have got those sedimentary rocks right, but they, for some reason, listed minerals and igneous or metamorphic rocks as possible answers. The only possible answers for the sedimentary rocks were the ones we looked at in the sedimentary rocks lab. This lab that we have coming up is going to be on relative dating, and I'm hoping that you will pay close attention to this video, because I'm going to show you how to do relative dating. And relative dating, as I mentioned before, is figuring out how old rocks are in comparison to the other geologic rocks or geologic bodies around them, be they sedimentary rocks, or which are always in beds, layers, or igneous or metamorphic rocks. And in order to do relative dating, I'm going to cover the main principles of relative dating, and those are superposition, the principle of superposition, the principle of original horizontality, the principle of lateral continuity, the principle of cross-cutting relationships, the principle of inclusions, and the principle of fossil succession. So in order to do relative dating, we need to have 6 tools in our toolkit, and you need to know how to use all 6 of these tools. Now, first let's talk about the first 3 principles are from a man named Nicholas Steno back in the 1800s. And you absolutely have to know how these work. So I'm going to show you some pictures here. First picture here is from Bryce Canyon National Park, Utah. And you see these spires of sedimentary rocks. Here you can see a bed of sedimentary rocks. This is a lighter colored one. And you can see other layers, but from now on we're going to call them beds. Sedimentary rocks are always laid down in these flat layers. And this picture shows you what the principle of superposition is about. When you're looking at sedimentary beds only, not igneous or metamorphic, the sedimentary beds on the bottom are older than those on top. I'll repeat that. The sedimentary beds on the bottom are older than those on top. So these beds here on the bottom of the spires would be older than those on top. But if you think about that, you don't even need to memorize that. It's common sense. If a sedimentary bed is deposited, let's say sandstone, and then the limestone's on top of it, and then there's a conglomerate on top of that, well, this bed here must have been formed first in order to form a surface upon which the next bed was deposited, and then that surface on top of that was another layer was deposited. So let's put that in practical terms. The principle of superposition states that when you are looking at stacks of sedimentary beds, the layers on the bottom are older than the beds on top. You got to get that always. Now, let's take a look at another situation here. Here's some actual rocks. The sedimentary beds on the bottom, let's say this is a limestone. This limestone bed would be the oldest. And this sandstone bed on the top would be the youngest. So this bed's the oldest, second oldest, third oldest, and the youngest. Second principle we need to learn about is called the principle of superposition. And the principle of the principle of original horizontality is the next one. And the principle of original horizontality from Nicholas Steno is quite simple. When sedimentary beds are deposited, in this case you have a sandstone, that's what these dots mean, and dashes mean shale, and this brick pattern is a limestone. So which bed is the oldest here? The sandstone, the shale, or the limestone? The sandstone is principle of superposition, right? And the youngest would be this bed of limestone. Principle of original horizontality states when sedimentary beds are deposited in a river or in a lake or wherever they're deposited, they are deposited flat and horizontal. So, if you see some sedimentary beds that are no longer horizontal, we know that they were originally horizontal and then something happened to them. Let's take a look at this one here. Let's say we saw beds that look like this, that were in folds like this, where the rocks are folded. Well, what must have happened was those sedimentary beds were deposited horizontal, according to the principle of original horizontality, just like this stack of pieces, these pieces of paper, and later on they were pushed together or compressed to make folds. So sedimentary beds are not deposited in folds. They're first deposited horizontal, and then they are folded by compressing them. Now, another way, let's take a look at another use of the principle of original horizontality. Let's say we have beds that are not horizontal. We know that they were originally horizontal, and then something happened to them. So if you had sedimentary beds that look like this, and believe it or not, you're going to be able to do the historical geology of this area with relative dating soon. Which beds are the oldest, A or K? A is on the bottom. The A must be the oldest beds, according to the principle of what? Superposition, right? And B is younger than A, and C is younger than B, etc. But these beds going from A to F here, they're not horizontal, they're tilted. But instead of saying tilted, we say they are dipping. So these are dipping beds. Let's say to the right is east and to the left is west. We could say the beds A through F are dipping to the west. How did you form these beds? Well, bed A was deposited, then B was deposited, then C, then D, then E, then F. And then beds A through F were tilted. How do beds get tilted? By an earthquake. So when an earthquake occurs, you can tilt beds. We know that these beds were not originally deposited tilted. They were originally deposited horizontal, and then at some later point they were tilted. That's the principle of what? The principle of original horizontality. Next principle we're going to look at is called the principle of lateral continuity, also by Nicholas Steno. The principle of lateral continuity states that, let's say, in order to understand the principle of lateral continuity, imagine that you're standing right here on top of this hill. And your friend, she is standing over here on the top of this hill. When you look down the hill slope, what do you see? You see this orange bed, and then you see this maybe yellow sandstone and a gray shale and another yellow sandstone. And your friend over there, he sees the same exact order of beds: sandstone, shale, sandstone, and whatever that is, conglomerate, let's say. But there's a valley in between the two of you. The principle of lateral continuity states that if you are at one location and see the same sequence of sedimentary beds as in another location, we know that at one time they were continuous. And you can see that these red dashed lines show that this shale bed, for example, was continuous and once looked like this. So these beds are actually folded, aren't they? They were originally deposited horizontal, later on folded. But here you can see, let's use all of the principles that we learned. The orange bed is the oldest, followed by this, followed by this, followed by the youngest bed, the sandstone. We know that because of the principle of superposition. The sedimentary beds are no longer, principle of lateral continuity states that they're no longer continuous because they were eroded probably by a river, but they were once continuous. So we know these beds once went like this in the past due to the principle of lateral continuity. Are the beds horizontal? No, they're not flat. They are folded. Here you can see they're folded, just like they were originally deposited horizontal and then they were folded. They were compressed like that. So we know because of the principle of original horizontality that these beds first were deposited. First this bed was deposited, then this, then this, then this. Let's say this is bed A, B, C, and D. Bed A was deposited, then bed B was deposited, then bed C was deposited, then bed D was deposited. Then beds A, B, and C were compressed and folded. Then a river cut through and removed this section of rock so that they're no longer continuous, right? So that's an application of the principles of relative dating there. We're going to do some actual problems that will help you do your lab. But before we do, I'm going to talk about the very important principle of cross-cutting relationships, which was first introduced to the world by James Hutton. So James Hutton did not only figured out that the principle of uniformitarianism, he also came up with the principle of cross-cutting relationships. Here you can see that a hill, and with the oldest rocks on the bottom and the youngest on the top. What is this thing here? This is an igneous dike. Igneous rocks and metamorphic rocks can cut through sedimentary rocks, such as this igneous dike cutting through this stack of sedimentary rocks. What happened? What was the geologic history of this area? First this bed was deposited, then this one, then this one, then this one, then this one, then the igneous dike cut through the sedimentary rocks. And the principle of cross-cutting relationships simply states that any geologic feature that cuts across another geologic feature or set of geologic features is younger than the features that it cuts across. And that's common sense too, as Thomas Paine would say. If something is cutting across something, it must be younger than what it cuts through. That's the principle of cross-cutting relationships. Let's take a look at another application here. And we need to get used to these symbols. When you see dashes, it means shale. Shale is a sedimentary rock, and so it's layered in beds. Brick pattern means limestone. And dots mean sandstone. Okay. So, which is the oldest bed here? The shale, the limestone, or the sandstone? The shale is the oldest bed according to the principle of superposition. But we also notice that when you see this pattern, this is called a stippled pattern, and you're going to see this over and over again, this stippled pattern. This feature cuts across beds C, B, and A. It's a dike, because whenever you have the stippled pattern means igneous rocks. So this plutonic igneous rock cuts across beds C, B, and A. What is intrusion D, or if you prefer, is dike D older or younger than beds A, B, and C? Dike D must be younger than beds C, B, and A, because it cuts across beds C, B, and A. This feature here, they mark with the letter E, is a fault. And so with a fault, you get everything on this side of the fault moved down this way, and everything on this side moved up this way. Is the fault older or younger than the dike? Well, the fault cuts the dike. So the dike had to be there in the first place in order to be cut by the fault. Right? So, I'm going to get you started here. Let's do the historical geology, the relative dating of this area. What happened first? You tell me what happened first. Shale C was deposited first, right? Then what happened? Limestone bed B was deposited. Then what happened? You tell me. You're just as smart as you're a smart person. You can do this. You're a very smart person. To figure it out, what happened next? Bed A was deposited, which is a sandstone. Sandstone bed A was deposited. So we'll just put bed in here just to make sure you know it's a bed. Then what happened? Tell me what happened next. Then dike D cuts through beds A through C. Isn't that what must happen next? Then what happened? Fault E cuts beds A through C and dike D. This is the correct answer. The relative dating for this cross section. This is a cross section, the surface of the earth, and this is what you see when you go deeper in the earth. For this cross section, this is the correct answer. Please try and get this answer yourself before you try and do the lab. Notice you always put the first thing on the bottom in historical geology. And I say it till I'm blue in the face, but somebody's going to put the first, what happened first on the top, and the oldest thing on the bottom. And you always want to put the first thing that happened on the bottom. Then what happened next comes here, until you work to the most recent event. Don't get it backwards, please. And look at this diagram and take out a blank piece of paper and see if you can get the right answer. If you can, you've gone the first step. If you can't, you got to keep doing it until you can do this. That's the relative dating for this section, using all of the principles we've learned. Fourth principle we need to know about is called the principle of inclusions. Principle of inclusion states that any rock body, any geologic body that, first of all, an inclusion is a little chunk of rock inside of your geologic unit. You have inclusions of sandstone. That's what these brown this brown with stippled with the dots is. You have chunks of sandstone in the granite here. And in this diagram here, you have chunks of the granite or inclusions of the granite in the sandstone. So this diagram here has inclusions of sandstone and granite, whereas this diagram to the right has inclusions of granite in the sandstone. Principle of inclusion states that the rock that contains the inclusions is younger than the rock from which the inclusions are derived. I'll repeat that. The rock that contains the inclusions is younger than the rock from which the inclusions are derived. Let's see if you understand that or not. Look at the diagram on the left. Which rock is older, the granite or the sandstone? Which rock is older, the granite or the sandstone? Your answer should be the older rock is the sandstone, because the granite contains the inclusions of the sandstone. In this situation here, which is the older rock, the granite or the sandstone? The older rock should be the granite, because the sandstone has inclusions of granite in it. So in this situation, the granite is the older rock and the sandstone is the younger rock. In this situation, the granite is the younger rock and the sandstone is the older rock. Why did they draw this reddish tinge here near the contact? The contact means the boundary between the granite and the sandstone. What they're showing here is that this rock was heated. Remember, granite is a plutonic rock, so it formed from magma deep in the earth. So in this situation, the sandstone was deposited, and then the granite cut through the sandstone, and chunks of sandstone fell into the magma chamber. In this situation, the geologic history is completely different. Granite's a plutonic rock, right? So it cooled underground. So there was other rocks there before, and the granite penetrated into those other rocks. Those other rocks were eroded away. And then at some later point, this sand was deposited, maybe in a river, maybe on a beach. But chunks of the granite were torn apart and incorporated into the sandstone. So these are two completely different geologic situations, and we can interpret them using the principle of inclusions. Before I go, last thing, principle of fossil succession. Principle of fossil succession was developed by a man named William Smith. And William Smith was a friend of Charles Darwin. And William Smith was interested in determining whether or not his friend's idea, whether or not evolution occurred according to Darwin. And he thought about it. Well, how could I test this? The scientists are always trying to figure out ways of testing hypotheses. And he thought to himself, well, if the principle of superposition tells us that the rocks on the bottom are older than the sedimentary beds on top, only for sedimentary rocks you can use that, then all I've got to do is go to different locations in England and Wales and Scotland and Ireland and France and Germany and look at the rocks on the bottom and then see, do the creatures change as you go to younger rocks? If they do change, that means they evolve. And yes, he did notice that species evolve or change. They might increase in body size, they might decrease in body size, they might become better swimmers. They evolve, because otherwise they would look the same as you go to younger and younger rocks. But he also noticed that when you look at older rocks, you always find the same fossils, the same types of fossils, like this trilobite. We'll talk about those later. Or this ammonite up here. So if you know, you can use fossils to figure out how old rocks are. And if you find rocks of the same age at two different locations, you can draw these lines in to show that, for example, this unit here and this unit here were formed at the same time, and this one here and this one here was formed at the same time. Let's use the principles of relative dating to do some geology here. Okay, we already did this one here. You should be able to do this one. And if you can't do that one, you need to study this a bit more until you get it. So let's take a look at this one here. Here's a very simple example. These dashes, when you have dash, dot, like that, that's siltstone. And brick pattern, limestone. Dots, sandstone. Dashes, shale. And this is igneous. This is a dike and a sill. What happened first? What would you write down here? I would write siltstone C was deposited. Then what happened? Limestone E was deposited. Then what happened? Sandstone D was deposited. Then what happened? Shale B was deposited. Then what's the last thing that happened? Dike A and a sill cuts through beds C, E, D, and B. That's what you should write here. It's quite a bit. Dike A cuts through siltstone C, E, D, and B. In order to go further, we must know what an unconformity is. And we talked about it before in a previous video. And unconformity is missing geologic time. This picture here shows you what an unconformity looks like in a cross section. We're going to be working with a lot of these cross sections. Unconformities are always represented by wavy lines. So keep a lookout for these wavy lines. These red arrows point to the unconformities in these three cross sections. And this type of cross section is called a block diagram because it looks like a block. It shows you from different angles as you go deeper underground. The three kinds of unconformities are disconformity, a angular unconformity, and a nonconformity. So once you identify the unconformity, you need to figure out what type of unconformity it is. Is it a disconformity, an angular unconformity, or a nonconformity? Please note, there is no such thing as an angular disconformity. There is only a disconformity, an angular unconformity, and a nonconformity. A disconformity is an unconformity where you have sedimentary beds above and below the unconformity surface, and they are dipping in the same direction. Dipping means tilting. They're dipping in the same direction. Here you can see 3 sedimentary beds, and on top of that, 2 other sedimentary beds. They're all dipping in the same direction, so we call this a disconformity. An angular unconformity is where you have sedimentary beds above and below the unconformity surface, but they are dipping in different directions. In these cross sections, east is always to the right and west is to the left. Please don't forget that. East is to the right and west is to the left. This is north and this is south this way. Anyway, sedimentary beds here are dipping to the west. Sedimentary beds above the unconformity are horizontal. They're flat beds. So, they are dipping in different directions. Sedimentary beds you have above and below the unconformity surface, but they are dipping in different directions. We call this an angular unconformity. Again, the stipple pattern means igneous rocks. So a nonconformity is a type of unconformity where you have igneous or metamorphic rocks underneath the unconformity surface, such as here, and you have sedimentary rocks above the unconformity surface. So a nonconformity involves igneous or metamorphic rocks underneath the unconformity surface, and sedimentary rocks above. All three of these unconformities, represented by these wavy lines, indicate that the land was uplifted through mountain building, and then rocks were eroded away. So these unconformity surfaces actually represent large amounts of geologic time, where the missing geologic time due to erosion. When you erode rocks away, that record of that time period at that location was removed. So the rocks here may have been formed before 300 million years ago. The rocks here may have been formed at 100 million years ago. And all the rocks in between 100 and 300 million years ago might have been removed. And all that's left is this erosional surface, which we call an unconformity. So unconformities represent uplift of mountain ranges and then erosion. Now, let's use our tools and see if you can do some relative dating. The best way of doing things is hands-on. If you're a young man and your father explained to you how to change the oil by writing it down on pieces of paper, you wouldn't be too satisfied, would you? You'd rather have your dad say, "Let's get under the car and let's take out the oil filter with a wrench. Let's drain the oil. Let's do it." Well, we're going to do it here. Here you have a cross section. Now I want you to do the relative dating here. See if you can do it. Okay? Bed T is a sandstone. That's what the dots are. Bed R is shale. That's what the dashes are. With these rounded pebbles, this must be conglomerate. Bed M is a conglomerate. Bed V is sandstone. And bed J, with these dashes, means shale. Which of these beds is the oldest? T, R, M, V, or J? Bed T must be the oldest because of the principle of superposition. How about fault GF? Does it cut across beds T and R? Yes, it does. So that this side moved down and this side moved up. So is fault GF younger or older than beds RT? It's younger because it cuts across beds T and R. It doesn't cut across M, J, and V, so fault GF must be older than beds M, J, M, V, and J. What type of unconformity do we see here? Is this A, an angular unconformity, B, a nonconformity, or C, a disconformity? Well, you have sedimentary beds horizontal above and below the unconformity surface. So this is a disconformity. You should be able to recognize this as a disconformity. With all of that, we should be able to do the geologic history of this area. Tell me what happened first. Bed what T was deposited. All right? Now what tell me what happened next. Bed R was deposited. Then what happened? Fault GF cuts beds T and R. Right? Then what happened? What do you think happened next? Oh, crap. What do you think happened next? Uplift and erosion formed a what? Disconformity. Then what happened? bed M was deposited. Then what happened? Bed V was deposited. The numbers are off here. Oh, shit. This should say 5. Here, this should be a 5. I don't know how to put a 5 in here because the computer program is messed up. So that's a 5. Bed M was deposited. Then what happened? Bed V was deposited. Then what happened? Bed J was deposited. This is your complete answer, ladies and gentlemen. That's what your answer should be. See if you can do that. Turn off after you're done the video, see if you can do it at yourself without the audio on, and then you'll have it correct. I'll do one more here. See if we can get this one right. Tell me what happened first here. Bed F was deposited. Then what happened? Bed E was deposited. Then bed D was deposited. Then bed C was deposited. Then bed B was deposited. Then what happened? Well, what must have happened next is what? Think about it. Intrusion H cut through beds F, E, D, C, and B. Then what happened? Fault A cut through beds F, E, D, C, and B. Then what happened? Dike G cut through intrusion H. Beds, all of the F, E, D, C, and B were cut by dike G. Then what happened? I'm sorry. Then what happens? The fault cuts through, then the dike cuts through. Then what happened? Well, then this is the surface of the earth here. So let's do one more. Tell me what happened here. Sandstone F was deposited, then limestone E was deposited. Then what happened? Dike D cut through beds F and E. Then uplift and erosion to form a disconformity. Then beds C and B were deposited. Then the fault cuts through beds F, E, C, and B. Uplift and erosion forming a disconformity. And then limestone bed A was deposited. Let me ask you a question here, see if you get this one right. See, later on, believe it or not, you're going to be able to do this. Let's take a look at a angular unconformity. Here, which of these two unconformities represented by these wavy lines is an angular unconformity? This one or this one? Well, here, this must be an angular unconformity because the beds here are dipping towards the east rather steeply, and above they're horizontal. Whereas this must be a disconformity, right? Because the sedimentary beds above and below are dipping in the same direction. Notice this is an igneous rock because you have the stippled pattern, and it's got inclusions of the limestone in it and the shale. This one has inclusions of the shale and the limestone in it. What's the historical geology of this? First, this sandstone was deposited, then the limestone was deposited, then the shale was deposited. Then the igneous dike cut through the shale and the limestone. So that's why there are inclusions of these rocks in it, meaning that this rock is younger than these two rocks that it cuts through. Then the sandstone, the limestone, the dike, and the shale were tilted. Right? Then what happened? Uplift and erosion, forming a angular unconformity. Then what happened? Then these two beds were deposited. Then what happened? Uplift and erosion, forming a disconformity. Then the shale bed was deposited. Okay, that's quite a bit here. So I'm going to write it down for you so you get, and Microsoft Word works better for that. So let's see if I can get that on. Or I could use Pages too, since this is a Mac. The correct answer for this is what happened first. The yellow bed, sandstone was deposited. Sandstone bed was deposited. Then what happened? A limestone bed was deposited. Then what happened? A shale bed was deposited. Then what happened? The dike cuts through limestone and shale beds. Then what happened? Then the sandstone, limestone, shale beds, and dike were tilted. Then what happened? Uplift and erosion formed a angular unconformity. Then what happened? Then a shale and limestone bed were deposited. Then what happened? Uplift and erosion formed a disconformity. Then what happened? Then a shale bed was deposited. Okay, in the next video we'll do more relative dating.